Okay, gentlemen, so today we're going to deal with the fifth of the 7 gas laws we're going to learn total. It's called the ideal gas law, and it is PV equals nRT. So the ideal gas law is the first one we're going to talk about that actually deals with changing numbers of particles. So up till now, we've dealt with pressure, volume, and temperature. Way back at the beginning of the gas unit, I said we'd be dealing with the physical properties, pressure, volume, temperature, and how they relate to the number of particles. So the N in PV equals nRT stands for number of moles, and moles is just a way of counting particles. P is for pressure, V is for volume, N is for number of moles, R is for a constant called the ideal gas constant, which we'll talk about in a little bit, and T is for temperature, and temperature here is also has to be in kelvins. For all the gas laws, temperature has to be in kelvins. So be careful about that. So how did we get this ideal gas law? It actually comes pretty much from the combined gas law. So your combined gas law, P1 V1 over T1 equals P2 V2 over T2. That combined gas law can be modified for when number of moles isn't constant, for when the amount of particles changes. And all you have to think about is what happens when you add more gas. What effect is it going to have? And it actually is fairly intuitive. As you add more gas, you get a bigger volume. So an increase in particles leads to an increase in volume. So that tells us that there is a direct relationship between particles and volume. As particles go up, volume goes up, which, again, very intuitive. Because of that, to show in equations, to show a direct relationship, we actually put one thing in the top of a fraction and one thing in the bottom of a fraction. So for number of moles, since volume is in the top of this, number of moles would go down here, N1 and N2. And from that, we can see that PV over Tn always equals a constant. So another way of saying that they're always equal is that they always equal a constant. So P1 V1 over T1 N1 equals P2 V2 over T2 N2. And all of these things always equal a constant. Well, that constant is what we call R, the ideal gas constant. And all it is P V over T N. And if you look at this, PV equals nRT is just a rearranged version of this equation. So all we did is, by we I mean people who are much smarter than I am, figured out that the ideal gas law can be, or excuse me, the combined gas law can be modified with number of moles, and it always equals a constant. And that constant, they figured out, is R. Now, R doesn't have, well, it does have some definite values, but it matters what units you use. And we will actually learn a couple different values for R because we're going to use several different units of pressure. So depending on what unit of pressure you're going to use, of course, the R constant will be different. So again, PV equals nRT, where P equals pressure, and this will be in kPa or ATM. We're not going to deal with torr or millimeters of mercury for ideal gas law problems because I don't want you to look up a bunch of different R values. Then V equals volume, and that's in liters. N equals number of moles. I don't know if N actually stands for number of moles, but that's how I remember it. T equals temperature. And that's always in kelvins. And R is the ideal gas constant. So R is different depending on the different units you use. And the only one we're going to change up or different is the pressure unit. The only different unit we're going to use is the pressure unit. So R, when you're talking about kilopascals, is 8.31 liter kilopascals per Kelvin mole. Yeah, it's a pain. There's nothing you can do about it. Units have, or constants generally have weird combined units. All it is, if you look at this, is it's what it equals. It equals volume times pressure divided by temperature times number of moles. So liters times kilopascals over Kelvin moles is just how it rearranges. So for use of kilopascals, it's that. For atmospheres, it's 0.0821 liter atmospheres per Kelvin mole. Usually I'd have you guys memorize the kilopascals one. On tests and quizzes, I will probably just give you the kilopascals one. However, since we're, doing online home stuff, it's not like you can't look it up. So be careful about what units of pressure you're using and use the appropriate R value to get your answer. So that's one thing to look out for. So this is the ideal gas law. And again, it's very, very useful for a lot of different situations because a lot of times the number of moles is changing of a gas. So the other interesting thing about this is if you know 3 of any of these 4 values, not including R is constant. So if you know pressure, volume, and temperature, you can figure out the number of moles. If you know pressure, number of moles, and temperature, you can figure out the volume. Basically, if you have 3 of the 4 measurements, you can figure out the 4th mathematically. And sometimes that's really helpful because it can be hard to measure all of those different aspects. So again, it can be quite helpful. So I'm going to go through a couple problems, and then I'm going to talk about why it's called the ideal gas law really quick at the end. And that'll be our intro. There is a PowerPoint that goes along with it. Go through the PowerPoint. It has pretty much the same information, but just make sure, you look through it, see if there's something there that might help you that I missed, because we know that could happen. So here's the first of the problems I've picked out to do. At what temperature would 2.10 moles of N2 gas have a pressure of 1.25 atmospheres in a 25-liter tank? Should you say in and not and in a 25-liter tank? But anyways, we have here, and again, I like to label my variables. We have a number of moles, we have a pressure, and we have a volume. Now we're using atmospheres, so that means R equals 0.0821. And again, that'll be liter atmospheres divided by Kelvin moles. So because we're using atmospheres, this atmospheres determines this R value. If we were using kilopascals, it would be the other way around. We'd use the 8.31 liter kilopascals per Kelvin mole. So our equation is PV equals nRT. We have all the variables except one. So we're looking for temperature. We have everything else, and we have the constant. So it's just a matter of rearranging the equation and plugging everything in. So rearranging for T, isolating T equals PV over NR. Again, just divided both sides by NR. And now we just plug in the numbers. Temperature equals the pressure, 1.25 atmospheres, times the volume, 25.0 liters, divided by the number of moles, 2.10 moles, times, and here's our R value, times R, 0.0821 liter atmospheres per Kelvin mole. So One of the reasons I like to write out the unit, the terrible, terrible unit of R, is because it allows me to see that I have rearranged my equation correctly. So if we look at crossing out units, atmospheres will cross out, liters will cross out, and then if you remember, and I went over this a while ago, something in the denominator of a denominator, so you have a fraction in the denominator, something in the denominator of that actually gets flipped to the numerator. It's like it's up here. So this moles and this moles cancel out, and you're left with kelvins over 1, which is what you want. You want kelvins. We want a unit of temperature. We want kelvins. So it's just a matter of now, again, pushing buttons on the calculator and getting it. Okay, so I've done the math, and we get the temperature equals 181.25 kelvins, but because of 3 sig figs, because I'm limited to 3 sig figs from my measurements in the question, I just went to 181 kelvins. Again, with temperature, you're going to get kelvins out. Don't label that as degrees Celsius. That would be quite wrong. Also, it's not degrees kelvins. It's just Kelvin. Kelvin's an absolute unit. It's not degrees. I won't mark you wrong for that, but it'll hurt my brain a little bit. So please just try to write kelvins without the degree sign. So that's an ideal gas law problem. I'm going to do one more, but pretty much that's what it is. You'll be given 3 of the 4, unknowns, 3 of the 4 variables. You'll have the constant. Just make sure you use the right constant. And then you plug it in and rearrange it. So here's another one. What mass of CO2 is needed to fill an 80-liter tank to a pressure of 150 ATMs? So this is a little more complex of an equation, and this is something that we would actually see, used. If you know anything about scuba diving or, anything with a fire extinguisher stuff, when they want to fill a certain amount to a certain pressure, they actually weigh the CO2. They weigh it out in, well, in this country, a lot of times in pounds, which is a disaster, but they weigh it out in grams or kilograms. They actually weigh the CO2, and you could get a, 5-pound CO2 canister or CO2 tank or a 10-pound CO2 tank. And yeah, I know, 5 pounds is approximately 2 kilograms, and that's a much better way of measuring, but we're in America, so America. But it is helpful to know exactly how much mass of CO2 you might need for something like this. So what mass of CO2 is needed to fill an 80-liter tank to a pressure of 150 atmospheres at 27 degrees Celsius? So a couple things about this. First of all, 27 degrees Celsius. We're going to change that immediately to Kelvin. So that's going to be 300 Kelvin. 2 plus 273 is 300 Kelvin. And that'll be our temperature. This will be our pressure. This will be our volume. And because of atmospheres here, our R value, again, will be 0.0821 liter atmospheres over Kelvin moles. So our temperatures in Kelvin, our pressures in atmospheres, our volumes in liters. Now, here's where this is kind of strange. If we look at our ideal gas law, PV equals nRT, there's no mass in there. That's not a thing that exists. You can't get mass from PV equals nRT, at least not directly. But you can get it indirectly because you guys know how to do molar conversions. You can convert grams to moles. So since you can convert grams to moles, that means what you're going to look for is how many moles you need, or convert moles to grams, is how many moles you need. We're going to look for N. So this means N question mark, and then convert to grams. It's not hard. It's just one extra step. But this is where you start to see some kind of tie-ins between the gas laws and everybody's favorite thing, stoichiometry. You have number of moles in there. Yeah, you can do stoichiometry with this stuff. And again, I told you when we talked about the 22.4 liters at STP, standard temperature and pressure, I told you we figure out how many moles or how, in other situations. Well, this is how you would figure that out. you could figure out how many moles are at any temperature and pressure now using the ideal gas law. So you can then figure that out and use that as a conversion factor in your stoichiometry. So we're going to rearrange this equation for N. N equals PV over RT. And again, here we have all the other numbers we need, so we just plug them in. N equals the 150 atmospheres. Times the volume, which is 80 liters, divided by our gas constant, 0.0821 liter atmospheres over Kelvin mole. And then finally, times our temperature, and our temperature is 300 Kelvin. And this is one of those situations where it gets a little weird with the sig figs, because 300 Kelvin looks like it only has one sig fig. But the number we got it from, this 27.0, that has 3 sig figs, and that's the measured number. So I'm going to pretend like we have 3 sig figs and not go down to 1. I think that's the proper way to do it. I wouldn't necessarily mark you wrong if you went to 1, like it's an understandable mistake, but converting from one unit to another doesn't change the number of sig figs. So now we have all the numbers, just a matter of doing the math. Okay, and if we do the math, we get 487.2 moles of CO2, which I then rounded to 3 sig figs for 487 moles of CO2. But this doesn't ask about moles, this asks about grams. So we get to do a molar conversion, everybody's favorite. Not a hard one, just moles to grams. So 487 moles of CO2 over 1. And then we're just converting to grams. CO2 is 44.01 grams over 1 mole. So if we do the math for that, do that molar conversion, we get 21,432.9 grams, which again, because of sig figs, we'd round to 21,400 grams. Or you could call it 21.4 kilograms if that makes you happier. It's a little easier to work with. Either of those answers has the right number of sig figs, and you can change the units from grams to kilograms. The question doesn't specify. So that is how you would do a couple gas law problems. These are just like the ones on your worksheet. There's nothing terribly difficult. Really, I think the hardest thing is just remembering which R value to use. Your worksheet will have both R values at the top, and it'll tell you in which circumstance to use them. Just be careful to check what the pressure is. If it's in atmospheres, use 0.0821. If it's in kilopascals, use 8.31. Okay, so this thing is called the ideal gas law, which is kind of an odd name for a law. Why is it an ideal gas law? So the reason it's called an ideal gas law is it only technically works with an imaginary thing called an ideal gas. So an ideal gas is something that has particles with no volume and no attractions or repulsions. Basically, the particles have no intermolecular forces and no volume. Of course, this doesn't exist. All gases, particles take up some space. However, because gases are spread out so far, because they are so non-dense, they're so spread out, they're under most conditions, real gases behave like an ideal gas. They're so spread out that the particles might as well have no volume. If something is if some gas is in a container and that container is 99.9999% empty space, the fact that the particles have that 0.00001% of volume is mathematically negligible. It just doesn't matter. Also, if the particles are that far apart and they're moving quickly because they're gases and gases are moving quickly, the attractions and repulsions, while they exist, are negligible. They don't really happen. Technically, they happen a little bit, or they're theoretically there, but they don't affect anything. They're just too weak to overcome the kinetic energy of the gas particles. So even though an ideal gas doesn't exist, the ideal gas law works with gases under the vast majority of conditions. In any sort of normal situation that human beings could exist in, for instance, so any of the conditions of temperature and pressure that we exist, or even any of the conditions of temperature and pressure that you would find pretty much anywhere on Earth, the ideal gas law is a really, really good indicator of what gases will do. Though technically, it is just an ideal gas estimate, because the particles do have volume, though it's mathematically negligible in most cases, and they do have attractions and repulsions, which again, under most situations, are so small as to pretty much not matter. However, there are conditions where the volume and attractions and repulsions, intermolecular forces, start to matter. So the ideal gas law does not predict what gases will do under conditions of high pressure, low temperature, and really anything that has high density, which both high pressure and low temperature can cause. So both the first two things can cause high density. So if we think about that, this actually makes a lot of sense. The particles of a gas generally don't matter. The size of them doesn't matter. The fact they have volume doesn't matter because the gas particles are so spread out. Well, if you put a gas under super high pressure, the gas particles are going to be pushed together. And the same thing happens at low temperature. Because they move much slower, they tend to clump together. So now suddenly, the amount of volume those particles takes up, it's not 0.00001% of the total volume of the gas. It's a significant percent, maybe 20, maybe 15, but a significant percent that would affect the math. Low temperature does the same thing, but also when you put those particles really close together and slow them down, those attractions and repulsions start to matter. That kinetic energy, at low temperature, kinetic energy goes way down. So attractions and repulsions, the intermolecular forces, start to have effects, which affects how gases exert pressure, for instance. So if they're more attracted to each other, they're not going to bounce around off the walls as much because they're clumping together because they're attracted to each other. And again, high density is just kind of the combination of high pressure and low temperature, or the thing caused by high pressure and low temperature. Again, you pack the gas particles together, suddenly their volume matters and their attractions and repulsions matter. It's just that under the vast majority of circumstances, both those things are, both particle volume and intermolecular forces are so insignificant that we can simplify what gas will do into the ideal gas law. So that's my ideal gas law intro. Hopefully you guys are having a good week. Lab is due Thursday. This worksheet is due Friday. And I will do some more problems in a couple days. Enjoy.